Hey everyone! In this video I'm going to talk about limits. So in other words, finding out the value of a function as its input moves closer to some value. Okay? And so limits are essential for social scientists' mathematical toolkit because we'll need them for two related tasks. First, we'll need them in calculus in order to minimize or maximize certain functions. For example, if you do if you use game theory or maximum likelihood estimation, they are ultimately based on limits. And lastly, a lot of very fundamental results in statistics and statistical inference are based on limits. And so to start with those two examples, two of the kind of most important theorems in statistics are ultimately based on limits of sequences. First, we have the central limit theorem, which basically states that for any series of independent and identically distributed random variables, x1, x2, and so on, the distribution of the sum of this set of random variables follows a normal distribution independent of the underlying distribution of x. And that's a central or one of the most important theorems in statistics. And it's based on the limit kind of as this sequence of random variables, x1, x2, x3, approaches infinity, but gets larger and larger. We can say that the distribution of the average or the distribution of x approaches a normal distribution. And here what this specific equation tells us is that here we're subtracting x bar, so the average of all the xn's, when we're subtracting the mu, which is the mean of x, and we're dividing by the standard deviation divided by itself by the square root of n. Basically, if we normalize these x's by subtracting the mean and dividing the standard deviation, then as n increases to infinity, this equation converges in distribution to a standard normal distribution with mean 0 and standard deviation 1 or variance 1. And we'll use this central limit theorem to derive a lot of to characterize uncertainty around a lot of our estimates. A second kind of fundamental, really important theorem in statistics is the law of large numbers, which states that for any draw of identically distributed independent variables with mean mu, the sample average after n draws, so x bar n, converges in probability to the true mean as n approaches infinity. Okay, so one way or a way to kind of express this mathematically or using mathematical notation is we have the sequence of xn bar of xn's, and we're looking at the difference between xn bar and mu, specifically the absolute value of that difference, right? And so as we increase n to infinity, the probability that this deviation of xn bar and mu is larger than some small epsilon is equal to 0. And another way of saying this is that xn bar is approaching mu or converges in probability to mu. All right. So those are two examples in statistics that fundamentally are based on limits and using limits to kind of characterize how certain sequences behave as we increase the number of elements to infinity. More generally, we also use limits to kind of describe how functions behave as they approach certain points. So for example, or in general, a function like f of x is always kind of some representation of, or as we said in the previous video, a mapping of some input x to that is a part of the domain into an output y that is part of some range. Okay, let's see. And in general, we can say that if f of x approaches some number that we now specify as capital L, as its independent variable x moves to some number c, so this could be 0 or plus or minus infinity, then we say that the limit of f of x as x approaches c is L. Okay, and so in mathematical notation, this looks like this. We see the limit of x approaching c of f of x is equal to L. Okay, so that's how we write the limit. F of x, that's important to note, f of x does not necessarily have to be defined at c for the limit of x approaching c to exist, right? So for example, when we have a function like 1 over x that is not defined at x equals 0 because you can't divide by 0, we can still find the limit of x approaching 0, both from the left side and from the right side of that function. There are a couple of important properties of limits. First, if we have two different functions, f and g, where the limit of f of x with x approaching c is equal to k, and the limit of g of x for x approaching c is equal to L, if we have this setup, then there are a couple of things that we can say about those two functions. First, if we look at the limit of x approaching c of the sum of those two functions, f of x plus g of x, then that limit is equal to the limit of the sum of the two functions that have a defined limit itself is equal to the sum of the limits. Second, if we just focus on f of x and multiply this f of x by some constant k, then the limit of that k times f of x is equal to k times the limit of f of x. If both functions are multiplied, so we have the limit of x approaching c for f of x times g of x, we can again separate those two and describe this as the product of the limit of f of x times the limit of g of x. And then if we have a fraction, so f of x divided by g of x, and take the limit of that for x approaching c, that is again the fraction of the two limits. So the limit of f of x divided by the limit of g of x, of course, provided that the limit of g of x for x approaching c is not equal to 0, because we can't divide by 0. There are different types of limits. I kind of mentioned this already when I talked about this function 1 divided by x. In general, what I mentioned there is that we can think about the limit approaching a certain, like as x approaches a certain value, from the left-hand side or from the right-hand side. So the right-hand limit is defined as the value approached by f of x when you move from the right to the left. So when you move from a value larger than c towards c. Okay. The left-hand limit, on the other hand, is the value approached by f of x when you move from the left to the right. So from a value that is lower than c up to c. And importantly, those are not necessarily the same, right? So as I mentioned, this function f of x equals 1 over x. As you can see here, it is not defined for 0 because we can't divide by 0. But for the right-hand limit, so the value approached by f of x when you move from the right to the left, so as x becomes smaller and smaller and closer to 0, the limit is infinity, so plus infinity. And if we look at the left-hand limit for x approaching 0, starting with values smaller than 0, the limit is actually minus infinity. Two other types of limits are infinity and negative infinity, and what we mean by that is basically just the value approached by f of x as x grows infinitely large or grows infinitely negative. Okay, so for the context, in the context of f of x equals 1 over x, the limit, the infinity would be, and the negative infinity would both be 0 as the function is approaching 0 as x approaches both plus infinity and minus infinity. Another important concept that we sometimes see that I just want to mention briefly is continuity. And it's also related to another concept called differentiability, which we'll cover when we talk a little bit about calculus. And in general, continuity can be defined as follows. Suppose that the domain of the function, so the set of values that are mapped onto some other set of the function f, includes an open interval containing the point c. So it's basically just this c is kind of part of the domain of f of x. Then f is continuous at c if the limit of x approaching c of f of x exists, so the limit has to exist, and the limit is equal to the function value f of c. Okay, so in other words, a function is continuous if the limit is equal to the function value, and the limit and the function value also exists. Okay. Further, we can say a function is continuous on an open interval a b if it is continuous at each point in the interval. Okay, so kind of to describe this more like intuitively, we can say that functions that have breaks in their lines are called discontinuous, and functions that have no breaks are called continuous, because as soon as they have a break in the line, then this kind of mathematical definition based on the limit being equal to the function value does not hold anymore. And just to kind of show you examples of how where this holds and where this doesn't hold, the two functions on top here, f of x equals square root of x and f of x equals e to the power of x, those are continuous functions. So f of x equals square root of x, of course, is only defined for x larger or equal than 0, because you can't take the square root of a negative number. But nevertheless, for the range, for the domain of x larger or equal to 0, this function is continuous, because at every point there's no break, or in other words, the function is defined at any point c and is equal to the limit of f of x approaching c. Same for e to the power of x across the whole range of x going from minus infinity to plus infinity. Lastly, these two functions on the bottom, f of x equals 1 plus 1 over x squared, or f of x equals floor of x, so basically just that function ultimately, just if you have 4.2 or 3.2, it just the floor function basically just reduces the number to the lower to the next integer, right? So 4.2 is changed to is mapped to 2. 4.2 is mapped to 4, or 4.8 is mapped to 4. 5.1 is mapped to 5. Okay, and so those are two examples of discontinuous functions because at this point here at x equals at x equals 0 for f of x equals 1 plus 1 over x squared, we see that we have a break in the line. That's kind of the intuitive way of describing this, but essentially what we also see is that that f of x, the limit of f of x as x approaches 0, of course, exists. That's infinity for this function, but it is not equal to f of 0, because f of 0 in this case does not exist. Okay, so that means we have a point where the function f of x equals 1 plus 1 over x squared is not continuous. Same for the floor function. All right, that's it for limits. In the next video, I'm going to talk about calculus.